Look up on a clear night, far from the glow of city lights, and you'll see it, the Milky Way. A river of stars stretching across the darkness, so vast that the light you're seeing left those distant suns thousands of years ago. Some of those stars no longer exist. They've already died, exploded, scattered their atoms across the void, but their light still reaches you. A ghostly message from the deep past that it's beautiful, humbling, and if you watch long enough, you might begin to feel something else. A connection, because you are not separate from those stars. You are made of them. Every atom in your body, the carbon, the oxygen, the iron flowing through your veins, was forged in the heart of a dying star billions of years ago. You are, quite literally, stardust given form. Stardust that learned to breathe, to think, to wonder. But the connection goes deeper than chemistry. There are forces at work, invisible, silent, reaching across unimaginable distances that bind everything together. Gravity pulls galaxies into slow spirals. Electromagnetic radiation floods the universe with light and energy. Particles born in stellar explosions drift for eons before colliding with something, somewhere, changing it in ways large and small. Nothing in the universe exists in isolation. Everything is connected by these threads, this great cosmic web that ties atoms to planets, planets to stars, stars to galaxies, and all of it, somehow, to us. Tonight, we're going to explore a question that sounds almost impossible, a question that sits at the intersection of astronomy, biology, and deep time. Could the celestial forces that govern the cosmos, the gravity of distant planets, the radiation from the sun, the pull of the moon, even the slow turning of galaxies, have influenced the evolution of life on Earth? Not in some vague, poetic way, but actually, measurably, physically. Could the rhythm of the heavens have shaped the rhythm of life itself? It's a radical idea. Evolution, as we understand it, is driven by random mutations and natural selection. Genes mutate, environments change, creatures adapt or die. Over millions of years, this process sculpts the diversity of life we see around us. But what if those mutations aren't entirely random? What if the environment isn't just oceans and mountains and weather, but also the invisible influence of celestial mechanics? What if evolution has been dancing, all along, to a rhythm set by the stars? Imagine the early Earth, 4 billion years ago, a world of shallow seas and volcanic islands, bathed in the light of a younger Sunday. The moon hangs closer in the sky, massive and bright, pulling enormous tides that flood coastlines twice a day. In those tidal pools, where water surges in and out with lunar precision, the first simple organisms are learning to survive. They must adapt to being submerged, then exposed, wet, then dry, safe, then vulnerable. The rhythm of the moon becomes the rhythm of their existence. Could that rhythm have left a mark? Not just behaviorally, but genetically? Could the predictable cycles of celestial mechanics have created evolutionary pressures so consistent, so relentless, that life began to internalize them? These are the questions we'll explore tonight, that we'll journey from the birth of the solar system to the present day. We'll examine the moon's gravitational embrace, the sun's radiant power, the slow dance of planets that tilt our world into ice ages. We'll look at cosmic catastrophes, asteroids and solar storms that reset evolution's clock. We'll even consider the invisible rain of cosmic rays that might, just might, be nudging mutations in ways we're only beginning to understand. This is not a story of certainty. Science is still unraveling these mysteries piece by piece. But it is a story of possibility, of wonder, of the profound realization that we are not just on this planet. We are of this universe. Every breath you take is timed by the rotation of the Earth. Every heartbeat echoes rhythms encoded over billions of years. You are a walking, thinking testament to forces that reach back to the beginning of time itself. So settle in. Let the weight of the day fall away. Feel the planet turning beneath you, the moon pulling gently at the oceans, the sun, even now, on the other side of the world, preparing to rise again. And let's begin, because if there's one thing the universe has taught us, it's this: nothing happens in isolation. Everything is connected. Everything influences everything else. And life, fragile, resilient, endlessly creative life, may be the universe's way of feeling its own rhythms. Let's go back. Way back. A time before cities, before forests, before even the simplest animals walked the earth. Back to when life itself was just beginning to figure out what it meant to exist. 4 billion years ago. Give or take a few hundred million. The earth was young, violent, a world of extremes. Volcanic eruptions split the crust, spewing gases into a thick, toxic atmosphere. Oceans were forming, gathering in vast basins as the planet slowly cooled. Asteroids still pelted the surface with brutal regularity. Remnants of the chaotic birth of the solar system. It was not a gentle place, but it was, crucially, a rhythmic place. Even then, especially then, the Earth was not alone. It danced to the pull of celestial forces just as it does today. Perhaps even more so, the moon was closer. Much closer. Perhaps 20 times larger in the sky than it appears now. Its gravitational pull was immense, dragging the oceans into tides that could rise hundreds of feet. Coastlines weren't stable. They were battlegrounds where water advanced and retreated with ferocious regularity. Twice a day, the tide came in. Twice a day, it went out. And in those narrow zones, the tidal zones, something remarkable was happening. Life was taking hold. The earliest organisms were simple. Single cells, bacteria and archaea, huddling in the shallow pools left behind by retreating tides. They had no brains, no organs, no awareness in any sense we'd recognize. But they had something else. They had chemistry. And chemistry, it turns out, responds to rhythm. When the tide came in, the water brought nutrients, dissolved minerals, organic molecules washed down from the land. Food. In other words, when the tide went out, the organisms were exposed. Sunlight hit them directly, dangerous ultraviolet radiation that could damage their fragile structures. Temperatures fluctuated. Salinity changed as water evaporated. Survival meant adapting to this cycle. Organisms that could sense when the tide was coming, or better yet, anticipate it, had an advantage. They could prepare, activate protective mechanisms, shift their metabolism, and so, very slowly, over millions of years, life began to internalize the rhythm of the moon. Biological clocks started to form. Not conscious timekeeping, but molecular, proteins and genes that oscillated in sync with the tides. When the moon was overhead, certain genes activated. When it moved on, they shut down. This wasn't learning. It was evolution. Organisms whose internal clocks matched the external rhythm survived better, reproduced more, passed their genes and their clocks to the next generation. The moon, in a very real sense, was training life to keep time. But the moon wasn't the only teacher. The sun, of course, was the ultimate power source. Every day it rose. Every day it set. And with it came light, warmth, and energy, photosynthesis. The process by which organisms capture sunlight and turn it into chemical energy may be the single most important evolutionary innovation in Earth's history. It transformed life from something that merely survived to something that could thrive, grow, spread across the planet. But photosynthesis only works when the sun is shining. When night falls, the process stops. Organisms must switch to different metabolic pathways to survive the darkness. And so, once again, life adapted to rhythm. A daily rhythm this time. The circadian rhythm, the roughly 24-hour cycle that governs nearly every living thing on Earth. Even bacteria have circadian clocks. Even organisms that live in total darkness, deep underground or at the bottom of the ocean, carry the genetic machinery for keeping time based on the rotation of the Earth. Why? Why would a creature that never sees sunlight need to know what time of day it is? Because its ancestors did. And that ancient rhythm, encoded in DNA, persists. A memory written in genes, passed down through billions of years. Then there are the seasons that as the Earth orbits the sun. Its tilted axis creates a yearly cycle of changing conditions. Longer days in summer, shorter days in winter. Temperature swings, shifts in rainfall. For life on land, especially, the seasons became an evolutionary crucible. Plants that couldn't time their growth to match the seasons died. Animals that didn't migrate, hibernate, or otherwise adapt to winter's scarcity went extinct. Over time, life learned to read the length of the day, the photoperiod, and use it as a calendar. Trees know when to bud. Birds know when to fly south. Deer know when to mate, so their fawns are born in spring, when food is abundant. All of this is guided by celestial mechanics. The tilt of the Earth, the orbit around the Sun, the predictable, unwavering rhythm of the heavens. And here's the profound part. These rhythms didn't just create environmental pressures that life had to respond to. They created predictable pressures, reliable pressures, pressures that repeated over and over with clockwork precision. This is what makes celestial forces different from other evolutionary drivers. That a volcanic eruption is random. A drought might last years or decades, but it's unpredictable. Predators evolve, prey evolve, ecosystems shift chaotically, but the sun always rises. The moon always pulls the tides. The seasons always turn. And so life, over deep time, could evolve not just to react to these forces, but to anticipate them, to build them into its very structure. Think about that. Your body doesn't just respond to light and darkness. It expects them. Your circadian clock is already preparing for dawn before the sun rises. Your metabolism shifts in anticipation of sleep. Even if you try to stay awake, you are not merely living on this planet. You are synchronized with it, with its rotation, with its orbit, with the ancient rhythms that have governed this world since the beginning. And those rhythms, in turn, are dictated by the cosmos. The Earth spins because of angular momentum from its formation. It orbits because of the sun's gravity. It tilts because of a massive collision billions of years ago, possibly the same collision that created the moon. Every force, every motion, traces back to celestial mechanics. And life, adaptable and relentless, learned to dance to every single one. But we're only beginning to scratch the surface. Because the celestial forces that shaped evolution aren't just about daily and yearly rhythms. There are deeper rhythms, slower, more subtle, rhythms that unfold over thousands, even millions of years. And those rhythms, as we'll see, may have sculpted the very path life has taken on this planet. Let's return to the moon for a moment. Because its influence on evolution goes far beyond tides and biological clocks, the moon is, in many ways, Earth's silent partner. It's been with us for nearly as long as the Earth has existed, born, most likely, from a catastrophic collision between the young Earth and a Mars-sized body called Theia. The debris from that impact coalesced into the moon, and it's been circling us ever since. But it wasn't always this far away. Billions of years ago, the moon was much, much closer. So close that it would have filled half the sky. Its gravitational pull was correspondingly stronger, strong enough to create tides that surged across entire continents. Imagine that world. Twice a day, walls of water sweeping inland, flooding vast stretches of land, then retreating hours later. The tidal zones weren't narrow strips of beach. They were enormous regions where the boundary between ocean and land was constantly shifting. And in those zones, life thrived. Because tidal zones are unique environments. They're harsh. Organisms must survive being submerged, then exposed to air. They must tolerate rapid changes in temperature, salinity, and oxygen levels, but they're also rich, nutrient-dense. Every tide brings fresh supplies of food and minerals. Evolution loves a challenge paired with an opportunity. Life in the tidal zones diversified. It adapted. And in doing so, it began to internalize the rhythm of the moon in ways that still echo today. Let's talk about spawning. Across the world's oceans, countless species time their reproduction to the lunar cycle. Corals, as we've mentioned, release their eggs and sperm in massive synchronized events timed to the full moon. Fish do the same. Crustaceans, mollusks. Why the moon? Because lunar cycles are predictable. They repeat every month with near-perfect regularity. For a species that needs to coordinate reproduction, ensuring that males and females release their gametes at exactly the same time so fertilization can occur, the moon provides a universal clock that communication needed. No complex behaviors, just a simple biological trigger. When the moon is full, spawn. This strategy has been so successful that it's evolved independently over and over in species separated by millions of years of evolutionary history. But it's not just marine life. Some scientists believe that the human menstrual cycle, which averages about 28 days, close to the lunar month, may be a vestigial connection to these ancient rhythms. The evidence is debated. The mechanism's unclear, but the coincidence is striking. And it raises a tantalizing question. Could our own reproductive biology still carry echoes of a time when our distant ancestors lived in rhythm with the moon? It's not as far-fetched as it sounds. Evolution is conservative. It doesn't discard what works unless there's a strong reason to. If our ancestors, hundreds of millions of years ago, when they were still aquatic creatures, evolved reproductive cycles tied to the moon, those cycles might persist in modified form even after we transitioned to land, even after we became mammals, even after we became human. The moon, in other words, may have left its signature not just in the tides, but in our very biology. And there's more. The moon stabilizes Earth's axial tilt. Without it, the Earth would wobble chaotically, and the climate would swing wildly between extremes. Seasons wouldn't be predictable. Ice ages could come and go in centuries rather than millennia. In such a world, complex life might never have evolved. The environmental pressures would be too erratic, too extreme. Evolution works best with challenges that are difficult but consistent. Random chaos just leads to extinction. The moon gave us stability. And stability gave evolution the time it needed to produce complexity. Trees, birds, mammals, us. None of it would exist without the moon. But the moon's influence isn't static. It's changing. Every year, the moon drifts a little farther from Earth, about 1.5 inches per year. It's a tiny amount, but over millions of years, it adds up. The moon used to be closer, and the tides were stronger. Days were shorter, the Earth spun faster. A day 4 billion years ago was only about 6 hours long. As the moon moved away, the tides weakened. The Earth's rotation slowed. Days lengthened. Life had to adapt to all of this. Species that had evolved around short days and strong tides had to adjust as the rhythm shifted, and they did. Because life is nothing if not adaptable. But here's the deeper question. Did these changes drive evolution forward? Did the gradual weakening of tides, the lengthening of days, create new niches, new opportunities, new evolutionary pathways? We don't know for certain, but it's possible, even likely, because evolution doesn't happen in a vacuum. It happens in response to the environment. And the environment, on Earth, is shaped by celestial forces. The moon pulls the tides. The sun drives the seasons. The planets tug at Earth's orbit. Asteroids rain down from space. All of it matters. All of it leaves a mark, and some of those marks, written in the genetic code of every living thing, point back to the moon, that pale companion that has watched over us since the beginning, shaping our world, shaping our evolution, shaping us. As you lie here now, the moon is somewhere above you. Even if you can't see it, even if clouds obscure the sky, it's there, pulling gently at the oceans, keeping time just as it always has, and somewhere, deep in your cells, ancient rhythms still echo its presence. If the moon is the timekeeper, the sun is the sculptor. Every form of life on Earth, every plant, every animal, every microbe, owes its existence to the sun. It is the ultimate source of energy for nearly all living things. Without it, the Earth would be a frozen, lifeless rock drifting through the void. But the sun's influence on evolution goes far beyond simply providing light and warmth. The sun is a variable star. Not wildly so. It's actually quite stable compared to many stars, but it does change. Its brightness fluctuates. Its magnetic activity waxes and wanes in an 11-year cycle. Solar storms erupt from its surface, sending bursts of radiation and charged particles hurtling toward Earth. And all of these variations have consequences. Let's start with the basics. Photosynthesis. About 2.5 billion years ago, a group of bacteria called cyanobacteria evolved the ability to capture sunlight and use it to convert carbon dioxide and water into sugar and oxygen. This was a revolution. For the first time, life didn't have to rely on chemical energy from volcanic vents or organic molecules floating in the ocean. It could tap directly into the sun's power. Cyanobacteria spread across the world. They formed vast mats in shallow seas. They filled the oceans with oxygen, so much oxygen that it fundamentally changed the chemistry of the planet. This event, called the Great Oxidation Event, was one of the most profound transformations in Earth's history. It poisoned many of the anaerobic organisms that had dominated the planet up to that point. But it also opened the door for new kinds of life. Organisms that could use oxygen to power more efficient metabolisms. complex life, as we know it, became possible. And it all started because a group of bacteria figured out how to harness the sun, but photosynthesis is just the beginning. The sun's light doesn't just provide energy. It also provides information. Plants use the quality and quantity of light to make decisions. Should I grow? Should I flower? Should I go dormant? In spring, as days lengthen and temperatures rise, plants detect the increasing photoperiod and respond by budding, leafing, blooming. In autumn, as days shorten, they prepare for winter, shedding leaves, storing energy, entering dormancy. This isn't random. This is evolution fine-tuning biology to match the celestial rhythm of Earth's orbit around the sun, but the sun doesn't always play nice. Solar storms, violent eruptions of energy from the sun's surface can unleash powerful bursts of radiation. When these storms are directed toward Earth, they can interfere with satellites, disrupt power grids, and even pose a radiation hazard to astronauts. But they also reach the surface. To a limited degree, most of the sun's harmful radiation is blocked by Earth's magnetic field and atmosphere. But some gets through, and when it does, it can interact with DNA. Ultraviolet radiation, for example, is a well-known mutagen. It can damage the molecular structure of DNA, causing mutations. Most of these mutations are harmful or neutral, but occasionally, very occasionally, a mutation confers an advantage, and that mutation can spread through a population, driving evolution forward. Could solar activity, then, influence the rate of mutation? Could periods of intense solar storms have accelerated evolution? It's an intriguing idea. Some scientists have proposed that fluctuations in solar radiation, combined with changes in Earth's magnetic field, might create windows of increased mutation rates. If true, this would mean that evolution isn't just shaped by life's struggle to survive in a given environment. It's also shaped, in part, by the activity of the sun, a force completely beyond life's control. Yet intimately tied to its fate, there's another way the sun sculpts life. Through climate, small changes in the sun's brightness, fractions of a percent, can have significant effects on Earth's climate over long timescales. During periods when the sun is slightly dimmer, the Earth cools. Ice sheets expand. Sea levels drop. During periods when the sun is slightly brighter, the Earth warms. Ice melts. Coastlines shift. These climate swings create evolutionary pressure. Species must adapt to new temperatures, new precipitation patterns, new distributions of food and habitat. Some adapt. Some migrate. Some go extinct. And in the wake of extinction, new species evolve to fill the empty niches. The sun, in this way, acts as a sculptor, not carving directly, but changing the environment in which life must survive, forcing evolution to respond. And then there's the question of life's origins. Many scientists believe that life began in shallow pools or tidal zones where sunlight could reach. The energy from the sun, combined with chemical reactions in the water, might have been enough to spark the first self-replicating molecules. If that's true, then the sun didn't just shape life after it emerged. It helped create it in the first place. From the very beginning, life has been a child of the sun, born in its light, sustained by its energy, sculpted by its variability. And even now, as you rest, the sun is still at work. On the other side of the planet, it's rising. Photons that left its surface 8 minutes ago are striking the Earth, warming the ground, awakening plants, signaling to countless organisms that a new day has begun. The sun never stops. And neither does evolution. But the sun is just one player in this cosmic story. Because there are other forces, quieter, more distant, but no less profound, that have shaped the path of life on Earth. Forces that unfold not over days or years, but over epochs. And those forces, as we're about to see, may have driven some of the most dramatic chapters in evolution's long history. Now we enter the realm of deep time, of rhythms so slow that they're invisible within a human lifetime, yet so powerful that they've reshaped the entire planet over and over again. These are the rhythms of planetary motion, the gravitational dance between Earth and its neighbors in the solar system, and they're written into the geological record and into the story of life itself that you've probably heard of ice ages. Periods when glaciers covered vast portions of the continents, when sea levels dropped, when entire ecosystems shifted toward the equator to escape the cold. But did you know that ice ages follow a pattern? That they come and go with a regularity that can be predicted? This discovery was one of the great triumphs of 20th century science. And it all traces back to a Serbian scientist named Milutin Milankovic in the early 1900s. Milankovic proposed that ice ages are caused by subtle, cyclical changes in Earth's orbit and rotation. These changes don't affect the total amount of sunlight Earth receives, but they do affect where and when that sunlight falls, and that makes all the difference. There are three main cycles, now known as Milankovitch cycles. The first is eccentricity, the shape of Earth's orbit around the Sun. Sometimes the orbit is nearly circular. Other times it's more elliptical, more stretched out. When the orbit is more elliptical, the difference in solar energy between the closest and farthest points becomes more pronounced. Summers in one hemisphere might be hotter, winters colder. This cycle takes about 100,000 years to complete. The second cycle is obliquity, the tilt of Earth's axis. Right now, Earth tilts at about 23.5 degrees. But that tilt oscillates between about 22 and 24.5 degrees over a cycle of roughly 41,000 years. When the tilt is greater, seasons are more extreme. When it's smaller, they're milder. The third cycle is precession, the slow wobble of Earth's axis, like a spinning top that's starting to lose momentum. This wobble changes which hemisphere is tilted toward the Sun during different parts of the year. The precession cycle takes about 26,000 years. These three cycles overlap and interact, creating complex patterns of climate change. When they align in certain ways, conditions become favorable for ice sheets to grow. Snow falls faster than it melts. Glaciers advance. The Earth enters an ice age. When the cycles shift, the ice retreats. The planet warms. Life spreads back into the regions that were once frozen, and all of this, every ice age, every interglacial period, every shift in climate, is driven by the gravitational influence of the other planets, particularly Jupiter and Saturn. Their massive gravity tugs at Earth's orbit, causing these slow oscillations. They don't mean to. They're not guiding anything. They're just there, existing. And their existence is enough to reshape our world. Now, here's where evolution enters the picture. Ice ages are challenges. They're environmental upheavals that force species to adapt or die. When glaciers advance, forests become tundra. Grasslands become ice. Coastlines shift as sea levels drop. Entire ecosystems are pushed south, compressed into narrow bands near the equator. Species that can't adapt go extinct. But those that can, those that evolve thicker fur or more efficient metabolisms, or new behaviors, survive. And when the ice retreats, those survivors spread out again, filling the newly available territory, diversifying into new forms. This pattern has repeated over and over throughout Earth's history. Each ice age acts as a filter, selecting for certain traits, culling others. And each warm period that follows is an opportunity, a chance for evolution to experiment, to fill new niches, to try new strategies. Some scientists believe that human evolution was profoundly shaped by these cycles. Our ancestors emerged in Africa during a period of rapid climate fluctuation. The Milankovitch cycles, combined with other factors, caused dramatic swings between wet and dry conditions. Forests expanded and contracted. Grasslands appeared and disappeared. These changes forced our ancestors to be adaptable, to learn to survive in multiple environments, to develop larger brains capable of solving novel problems in other words. The gravitational whispers of Jupiter and Saturn, mediated through Milankovitch cycles, may have helped make us human. It's a humbling thought that our intelligence, our creativity, our very sense of self, might owe something to the orbital mechanics of distant planets we can barely see with the naked eye. But that's the nature of the cosmic web. Everything is connected. Every force, no matter how distant, can have consequences. And the deeper we look, the more connections we find. There's evidence that mass extinctions, those catastrophic events that wipe out large portions of life on Earth, sometimes correlate with periods of intense orbital change. When the climate swings become too extreme, too rapid, species can't adapt fast enough. The result is extinction. Widespread, devastating, but also creative, because every extinction opens the door for new forms of life. The dinosaurs died, and mammals rose to dominance. Trilobites vanished, and fish diversified, destruction and creation intertwined, and behind it all, the silent dance of planets. Orbiting, tugging, shifting Earth's path through space by fractions of a degree that its evolution on a cosmic scale. Not just the evolution of species, but the evolution of the entire biosphere, shaped by forces that reach far beyond the atmosphere. And those forces, as we'll see next, aren't always gentle. Sometimes, the cosmos doesn't whisper. Sometimes it strikes.